NASA's newest map-combining telescope is rewriting the rulebook of what we can see in the universe. From revealing hidden star nurseries to mapping dark matter with unprecedented clarity, each breakthrough pushes the boundaries of discovery, and number one is something almost nobody guesses. Imagine a single image that stitches together observations from dozens of space telescopes, creating a seamless, three-dimensional map of the night sky. By combining optical, infrared, and ultraviolet data, the new instrument fills gaps that once left astronomers guessing about the true shape of distant galaxies. This unified survey not only sharpens our view of familiar constellations but also reveals faint structures hidden behind interstellar dust. Researchers can now trace the evolution of stellar clusters across billions of years with a continuity that was previously impossible. The result is a dynamic atlas that updates in real time, letting scientists compare historical records with fresh observations, and enabling citizen scientists to explore the cosmos from their own homes. In essence, the telescope acts as a cosmic stitching needle, weaving together the universe's story thread by thread.
Surprisingly, the telescope's combined spectrographs can isolate the faint signatures of gases swirling around distant worlds, even when those planets are lost in the glare of their host stars. By merging data from multiple wavelength bands, it amplifies the subtle dips in starlight that indicate the presence of water vapor, methane, or exotic metallic compounds. This capability pushes the search for potentially habitable exoplanets into a new era, allowing astronomers to compare atmospheric compositions across dozens of systems in a single observing campaign. The instrument's precision also helps differentiate between true biosignatures and false positives caused by stellar activity. As a result, scientists can prioritize the most promising candidates for future missions, refining the roadmap toward answering the age-old question, are we alone?
Astronomers have long relied on indirect clues to map the invisible scaffolding of dark matter, but the new telescope's ability to overlay gravitational lensing data from several observatories sharpens those clues dramatically. By synchronizing measurements of how massive galaxy clusters bend background light, the instrument produces a high-resolution dark matter portrait that reveals filaments and voids with unprecedented detail. This composite view supports simulations that predict how dark matter shapes galaxy formation, offering a rare chance to test theoretical models against real-world observations. Moreover, the enhanced lensing maps help identify regions where dark matter density peaks, guiding future deep-field studies aimed at uncovering the particles that make up this mysterious substance.
Hidden within thick clouds of dust, newborn stars have always been difficult to observe, yet the telescope's infrared channels, merged with radio data, pierce those veils to reveal stellar nurseries in vivid detail. By aligning observations from space-based and ground-based arrays, scientists can watch protostars accrete material and launch jets in near real time. This multimodal approach captures the entire life cycle of star formation, from cold gas clumps to blazing main-sequence stars, allowing researchers to quantify how environmental factors influence stellar mass distribution. The resulting maps not only enrich our understanding of how our own sun began, but also inform models of galaxy evolution across cosmic time.
Finally, the telescope's synchronized photometric arrays provide a more reliable rung on the cosmic distance ladder by cross-checking type Ia supernova brightness across multiple filters. By merging light curve data from several platforms, the instrument reduces systematic uncertainties that have plagued previous measurements of the universe's expansion rate. This refined calibration helps reconcile the current tension between different estimates of the Hubble constant, offering a clearer picture of whether new physics or observational bias is at play. In turn, a more precise expansion rate sharpens predictions about the ultimate fate of the cosmos.
Meanwhile, the telescope's rapid response network stitches together alerts from gamma-ray detectors, neutrino observatories, and optical surveys, creating a unified alert system that pinpoints fleeting cosmic explosions within seconds. When a gamma-ray burst or kilonova erupts, the combined data streams enable astronomers to triangulate the event's location with far greater accuracy than any single instrument could achieve. This synergy not only speeds up follow-up observations, but also enriches the scientific payload, allowing researchers to study the physics of extreme environments, such as the formation of heavy elements in neutron-star collisions, in unprecedented detail.
Remarkably, by integrating polarization measurements from radio and optical telescopes, the new system maps the Milky Way's magnetic field across the entire sky. These combined maps reveal how magnetic forces guide the flow of interstellar gas, influence star formation rates, and affect cosmic ray propagation. The comprehensive picture challenges earlier assumptions that magnetic fields were merely a peripheral factor, positioning them as a central player in galactic dynamics. Researchers can now test theories about how magnetic turbulence shapes the large-scale structure of our galaxy, opening avenues for deeper exploration of magnetohydrodynamic processes.
Beyond the stars, the telescope's fused spectroscopic surveys dissect the composition of the interstellar medium, identifying variations in dust grain size, gas temperature, and chemical abundances across vast regions. By merging ultraviolet, optical, and far-infrared spectra, scientists can track how elements cycle between stars and the surrounding medium, shedding light on the processes that enrich future generations of planetary systems. This holistic view also helps calibrate models of how light is absorbed and scattered, improving the accuracy of distance measurements and the interpretation of distant galaxy observations.
Incredible new composite images combine X-ray data with radio interferometry to chart the environments surrounding supermassive black holes and hundreds of galaxies. By aligning these disparate observations, astronomers can study how jets interact with surrounding gas, how accretion disks evolve, and why some black holes remain dormant while others blaze as quasars. This large-scale survey provides statistical weight to theories about black hole growth and its feedback on host galaxy evolution, offering clues about the co-evolution of galaxies and their central engines over billions of years.
Ultimately, the telescope's integrated sky map serves as a foundational dataset for planning the next generation of space missions. Mission designers can simulate trajectories that avoid bright foreground objects, target optimal observation windows, and predict background radiation levels with greater confidence. By feeding this comprehensive map into mission planning software, agencies can maximize scientific return while minimizing risk, ensuring that future telescopes and probes launch with the most informed view of the universe already at their fingertips.
We've explored how this revolutionary instrument is stitching together the sky, probing alien worlds, unveiling dark matter, and even guiding future missions, a testament to humanity's endless curiosity. Subscribe so you don't miss the next mind-blowing list, released weekly, that dives into the frontiers of science. Which of these 10 ways impressed you most? Let me know in the comments below, and if you enjoyed the journey, give this video a like. Thanks for watching, and keep looking up.